Wait a minute. Jackie didn't get to see that.
Well, no, it wasn't me.
See what?
You didn't see that, did you?
What, him click the screen on and say, hello, I'm Josh Locus.
Sweet.
We'll do it again, a little more. That's magic. You guys want to see that again? One more time.
You going, Fred?
Yeah, we're recording.
Alright, I'm Joshua Solomon, and I'm representing voltage generation stations through Locus. I'm also here representing Jason McCroskey, Rick Brown, and Joshua Rogers. We're going to start with the system overview, then the steady state operating curve, step response experiment model, sinusoidal input method, relay input method through Locus, and then summary conclusions. So here we have our manipulated variable. Input is percent, which is the voltage system. Comes out, control variable, voltage. We have the action element, gives the controller, gives the transmitter, turns on light bulbs. Here we have voltage station constant input for 94%. See it starts ramping up slowly, building up voltage until it gets to 90. It's called the transient period, and it goes steady state from there on out. Here you see our steady state operating curve. Not too bad. The average slope is 1.5 volts per percent. It's also our gain. The output of the voltage system depends on the effects of hysteresis. And let me explain this a little bit. So originally our very picky customer, this guy right here, said that this point right here was terrible because it was showing up like right here. So we tested this thing over and over again. What we kind of concluded was, if you first run the test, you go up, it starts ramping up to, what do we want, output of 80, goes up, gets there. Now if you keep running other experiments and you have it go past 80, you have it go to the highest output you got, which is 95, and then you tell it to go back and run another test to get this value, it's going to do something like this, and you're not going to get the same value. So that was very, very challenging here. It's the multimedia right there. Here we have the voltage station step response. This is 85 to 88% input. You have the input comes in, 85, 10 seconds it steps up to 88. The output comes along, steady state. Once it gets to 10 seconds where the input jumped up, it goes to this transient period here until it's reach steady state around 80 minutes. We do that for all of our ranges, and we come up with our step response gain. And here you can see that the gain for the step up is approximately the same, step down is approximately the same. It's a different story for the dead time and time constant. When you look at the up and the down, you can see it almost looks like you could draw a straight line. In fact, it would be very interesting to compare the rest of this data to what the red team has, so that we can see if, it did kind of like had a trend of falling. It's the same for the time constant. You can see, for example, the up falls down. Then for our modeling, we had the manipulated variables function was described by this. And with the transfer function came out. And these are the parameters that we used for our modeling. This is an example for the 85 to 88%. You can't see the model input because it's so perfectly matched here by the model output. But when we get to the experimental output, you see it runs in this purple, nice smooth, what you kind of would hope to expect. The experimental input kind of comes along and almost acts as if all of a sudden it was being treated like the input and just stepping up, without even going through some transient period and kind of going along there. These are the average values that we got for the experiment and for the model. In conclusion, for the step response, the gain is constant if for over increasing input, and the dead time and time constant decrease linearly over increasing input. Here we have the sine response. As the output starts ramping up, it goes through a transient period, and it reaches steady state. It has this nice sinusoidal response. we measure the amplitude and phase shift. To create our Bode plots, here we have the amplitude ratio versus frequency for the previous slide, 85 to 88% input. Starts at about 1 and looks kind of linear as it falls. Here we have the phase angle versus frequency. Again, it starts kind of linear and then it quickly drops off. Here we tried modeling the Bode plots. The problem we had with this model was that you can see the blue dot is the amplitude ratio data, and the model here doesn't quite follow that, but beggars can't be choosers. It's the best we got. K is 1.7 volts per percent, and tau is 0.12 seconds. Now this model follows it much more closely, which is kind of confusing because the previous slide was so off. We came up with a dead time of 0.03 seconds. Here's a table that shows all of our sine response results. Now moving on to the relay response. Here we have a set point was 94 volts, or 94%. You have the output coming up following this, and if you zoom in on one of these sections here, because it's so dense, what you see is that the input is going to a ceiling value and then dropping to a floor value, and the output is responding to that in this sinusoidal way. These are the values we measured here. You have the amplitude, the period, and the time between the peak of the output and input. Now, important things to look at here are the ultimate gain and the frequency. Take note of these values. We have the average of 1 and 1.2 for the two ranges that we did, and 6.2 and 5.2 for the same ranges. This is the open loop transfer function that we used for creating our root locus data. Here's an example of root locus plot. And you can describe this region here, it's overdamped, and then all these regions from critical dampening to ultimate gain, you have an underdamped region. In between, we have 1/500th K, 1/10th K, and 1/4th of K. Using these parameters for the 85% to 88% input, off that graph that you just saw, we got a KCU of 0.8 or 8, a quarter decay of 5, 1/10th decay of 4, 1/500th decay of 0.17, and critical dampening of 0.8. Now, if we compare that to the Bode and relay, in this table here, create these figures, you see that the data that we received from root locus and sine were very similar for both the ultimate gain and frequency. Then the relay was very far off. In conclusion, the root locus and Bode plot results are similar. For a response, customers should request a proportion controller with a KC of 7.7% volts to 0.8% volts, 5 for quarter decay, 3.8 for 10th decay, and 1.7 for 1/500th decay. Are there any questions?